Today we will be talking about errors again. We talked about errors in our last unit when we were using the alternating series remainder theorem. Back then, we had a series that was alternating in sign, decreasing in magnitude to 0. And so if we used, say, 5 terms in an approximation, then we would be using the next term in the series as the upper bound of the error. So that would be the most that the error could be in making that approximation. With Taylor's series, we are also going to be using a set number or a given number of terms to approximate the sum of the series, and we will be able to find something about the error made when we make that kind of an approximation. So again, alternating series remainder theorem is still in effect. It is our most accurate low minimum. It minimizes the error. So if our series is, and sometimes our Taylor's series is alternating in sign and decreasing in magnitude to 0. And if it is, we will still use the alternating series remainder theorem. But for this particular section, we will be looking at what happens if what happens if our series is not alternating in sign, decreasing in magnitude to 0. We will still be able to find an error bound, an upper bound for the error, using Lagrange error bounds. Okay, it was a long-winded intro to this. Okay, in this box on your notes, I have the rigorous Taylor's theorem, also known as the Lagrange remainder theorem, and I'm not going to focus a whole lot on it because in the past it has confused kids. Mainly what has confused kids is this little thing right here, that little z, and they're like, what the heck is that z? But I do like it, and for those of you who want to analyze this theorem, you go right ahead. It's really not too bad. But I'm going to jump ahead to how we use this theorem, because that theorem looks very complicated, okay? In use, though, it is really very simple. Really very simple to use. I like to think of Lagrange error as almost the first unused term in the Taylor series in your approximation. So you're going to approximate, again, you're going to approximate it with, say, 5 terms. Well, the Lagrange error bound is almost the 6th term. Almost, okay? Not exactly. We still will use this form. That is the form of every term of a Taylor's series, right? Nth derivative, x minus c to the n factorial. The difference is this nth derivative. For the Taylor series, we always find the nth derivative at c, at our center, right? Well, that is not true for the error bound. Instead, we will find the maximum that the nth derivative can be in the interval from the given x value in your approximation. Say you're approximating f of 2.2 or whatever. 2.2 would be your x value to the c value. So it's the maximum that the nth derivative can be in this interval. Okay? Almost the first unused term. So every Lagrange error bound will have this form. The maximum nth derivative in that interval times x minus c to the n divided by n factorial. N, here I'm using n to be the first unused term. Okay, it's the next term. It's the n of our next term. One thing that I've seen kids make a mistake in is that they still put x's. You will have no x's in your error bound. No x's in your error bound. You're always going to fill that in with a number. It'll be the number, again, it'll be the number that they tell you to approximate the function value at. Okay? Alrighty, let's look at some examples then. Okay, in this first example, I have a little FRQ example. So they give us f has derivatives of all orders for all real numbers x, and then they give us some values. And we've seen this before in problems up until now. They give us the function value at 2, they give us the first derivative at 2, the second derivative at 2, and the third derivative at 2. So I know already, I don't even have to read the problem. I know that they're going to have me write a Taylor's series for this, or a Taylor polynomial for that. And in part A, write the third degree Taylor polynomial for f about x equals 2, not a surprise. And then we're going to use it to approximate f of 2.3. So the Taylor polynomial will approximate f of x. Okay? And then we're going to use the Taylor polynomial to approximate f of 2.3. So we'll be putting 2.3 in for x. Okay? First, the third degree Taylor polynomial. We start with the constant term, 6. And then we go to our derivative terms, and we start with the first derivative times x minus c to the first power divided by 1 factorial, plus the second derivative times x minus c to the second power divided by 2 factorial. Every term in the Taylor series has that form, right? Including the error. That's the good thing about this, including the error. The error will also have this form. Okay. 8, the third derivative, times x minus c to the third power divided by 3 factorial. And that is the third degree Taylor polynomial for f about x equals 2. Now we're going to use that to approximate f of 2.3. So f of 2.3 will be approximately 6 plus 4 times 2.3 minus 2. I could have made that 0.3, right? Minus 7 times 2.3 minus 2 squared divided by 2 factorial, or just divided by 2, plus 8 times 2.3 minus 2 cubed divided by 3 factorial. Since this is an FRQ, that's a safe stop spot. I'm just going to stop right there. Okay? Alrighty. Part B. The fourth derivative of f satisfies the inequality, and look at this mess. Satisfies this inequality. It says the absolute value of the fourth derivative is less than or equal to 9. Get used to seeing this format, because when they give you this, they are giving you the maximum or max fourth derivative is 9. They're telling you that the maximum fourth derivative is 9 right there. Okay, that I already know. Whenever I see this format, I know I'm going to be doing Lagrange, and I sure am. Okay, it goes on to clarify that this is the maximum fourth derivative for all x in the closed interval from 2 to 2.3. From our c value to our given x value that we approximated f at. Okay? That is specifically what we need in Lagrange. Okay? Use Lagrange error bound on the approximation of 2.3 found in Part A to find an interval in which the exact value of f of 2.3 must lie. When they want an interval where this must lie, we are looking for something in this format. F of 2.3 is between, it'll be equal to, but or less than or equal to there, It's between two things. We want to find out the interval, so we're finding out where f of 2.3 is between. Okay? So that's what we're looking for. First Lagrange error. We used the third degree Taylor for our approximation. So we will use the fourth degree term for our error bound. So the error bound is, and I'm just going to write it in the exact same form that we used for our approximation and for our terms here. It's going to be the maximum error times x minus c, where c is 2 and x is 2.3. X minus c to the fourth power divided by 4 factorial. That is the Lagrange error bound. That is the Lagrange error bound. Okay? I am going to call that E for error. Okay? I'm going to call that E for error. And now I'm going to write my interval in which the exact value of f of 2.3 must lie. So f of 2.3 must be between, okay, this was our approximation. So I know f of 2.3 is going to be close to this, right? Close to this. I am going to call that A for approximation. Okay? It's going to be close to A. It's going to be close to A, but this is our error. This is a small number. Okay? It's going to be less than A plus E, the small error, and greater than A minus E. That's how that works. That's the error in which f of 2.3 must lie. That's it. Okay, part C. I threw in part C just to make this more of an FRQ style and to get a little practice. They give us that g is f prime of x, and we're asked to write the second degree Taylor polynomial for g centered at x is equal to 2. Okay, g is f prime of x. Here's f, and we want f prime of x, right? I'm going to do something here so that I can fold this over and so we can see f. Here is f. I just want to be looking at, okay, there's f, and we want for g to be f prime. All we have to do is take the derivative of that. Right here. We take the derivative of that, we will have f prime, and therefore we will have g. So the derivative of 6 is nothing. Now we come to this term. What's the derivative of this term? Well, I'm going to need to use a little chain rule here. So 1 times 4 is 4. X minus 2 to the 0 will be just a 1, and then the derivative of the inside is 1. So if you want to, you can make that x minus 2 to the 0 times 1, or you can just leave that as a 4. Okay? Okay. Now to the next term. 2 times a negative 7 will be a negative 14. X minus 2, decrease your power by 1. Don't forget to multiply by the derivative of the inside. Here it's just a 1, but be careful with that. Still divided by 2 factorial. Next term, 3 times the 8 is 24. Decrease your power by 1. Multiply by the derivative of the inside. All divided by 3 factorial. And that is not cleaned up, but you know what? I'm just going to leave it like that because this is an FRQ. That is a second degree Taylor polynomial for g about x equals 2. Okay? Alrighty. So a nice little FRQ using Lagrange. Let's take a look at some multiple choice possibilities, what you could be asked. They tell us that the function f has derivatives of all orders for all real numbers, and it is known that, and here is our form again, it is known that the maximum fourth derivative is 7/5 and the maximum fifth derivative is 3/4 for 0 to 2. Okay? Let P sub 4 be the fourth degree Taylor polynomial for f about x equals 0. The Taylor series for f about x equals 0 converges at x equals 2. Of the following, which, I need to correct that, it should be is, which is the smallest value of k for which the Lagrange error bound guarantees that the error in the approximation, this is just another way to say error, the error is less than or equal to k. They tell me to use Lagrange. This will be the Lagrange error right here. Okay, that is going to be our Lagrange. K is our Lagrange error, and that's what we're finding. So, we used the fourth degree Taylor in the approximation, so which degree should we use for our error? Well, we use the next one. So we use the fifth degree. So they gave us this, but we are not going to need it. That was there to sidetrack us. We're going to use the fifth degree term for our error. So the maximum derivative is 3/4 times x minus c. Okay, did they give me an x value? They give me an x value here, because I remember we shouldn't have x's in our answer, right? In our Lagrange error. I know we're centered at 0. Did they give me an x value? They sure did. The x value is 2. Okay? To the fifth power, because it's the fifth degree term, don't forget we're dividing by 5 factorial. And then I know that's the Lagrange error. I know that's my answer, but I need to know which of these it is. Which of these is it? I see the 3/4 over there on these two. 2 to the fifth over 5 factorial will be it. Okay? All right, so that's one way they could ask you a multiple choice question on Lagrange. Here's another way I've seen. I got these on AP Classroom. Let P of x be the third degree Taylor polynomial for a function f about x equals 1. There's our c value. Okay. Information about the maximum of the absolute value of selected derivatives of f over the interval from 1 to 1.2 is shown in the table above. Okay, of the following, which is the smallest k value for which the Lagrange error bound guarantees that this error is less than or equal to k? So, which is the smallest k value? We are looking for, again, we're just looking for the Lagrange error bound. Okay, so we'll set it up. We're using the third degree Taylor polynomial for our approximation. So we're going to be using the fourth degree for our error bound. So that's the one I want to pull out. My maximum error is 20. X minus c. X is 1.2. C is 1. And the power will be 4 because we're on the next degree term, yeah? And then we'd still need to divide by the factorial, 4 factorial. And I need to know which of these is that, so we'll have to work this out. No calculator, likely no calculator on this. This is 20 times 0.2 to the 4th over 4 factorial. 4 factorial is 24. 0.2 is 1/5, right? So we have 20 times 1/5 to the 4th power divided by 24. Well, I'm going to take that 5 to the 4th down to the bottom, and I'm going to write that as 5 times 5 cubed. I'm doing that because I can reduce the 20 and the 5 there. And then 24 is 4 times 6. And now I can reduce this 20 is 5 times 4, leaving a 1 up on top. So we have 1 divided by 125 times 6, which is 1 over 30, carry 15, 750. Okay, D. Alrighty. So another type, I've seen a couple of those on AP Classroom as well. Number 4. The function f has derivatives of all orders for all real numbers, and the 7th derivative of f is e to the sine x. Exactly. In this one, they didn't give me a maximum derivative, did they? They just gave me the function for the 7th derivative. If the 6th degree Taylor polynomial for f about x is equal to 1, there's our c value, is used to approximate f on the interval from 0.5 to 1, what is the Lagrange error bound for the maximum error bound on the interval from 0.5 to 1? What is the Lagrange error bound? Okay, so they didn't give me a lot of the detailed information that they have in the previous 2 examples, but we're still going to work this out. I know I need a maximum derivative. My problem is I have the exact function for the derivative. So I have to ask myself, what is the maximum that this can be in this interval? What would be the maximum that it could be? Well, our e to something power, I know that e to sine x will be on this interval. So sine x on this interval from 0.5 to 1, that is from 0.5 to 1, here's sine, right? Well, this is pi over 2, and that is bigger than 1. This is 0, and that's less than 0.5. So this is somewhere in here, right? Somewhere in there. And I know that it's the most it could be at 1, right? So this thing is the largest that it could be at e to the sine of 1. Okay? So when x is 1, this is the biggest it could be. So e to the sine of 1 is the biggest that the 7th derivative can be in that interval. Okay? A little confusing, but that's it. Okay? Times x minus c to the 7th power, right? I know what c is. Okay? So what would make this thing, so what is, they're not giving us the exact value of x, but if we want the maximum error, we certainly don't want to put a 1 in here if we want the maximum error, because that would make the error 0. The maximum error would be when x is 0.5, okay, divided by 7 factorial. A little confusing, okay? And one other thing, error is always positive, so I'm looking at this and I'm going to get a negative number for that, but I know it's always positive, so we're taking the absolute value of that. So this will be e to the sine of 1 times positive 0.5 to the 7 divided by 7 factorial. So a here. Alrighty? That was probably the most confusing one on this page, okay, that I've seen. That's the most, I got that directly, well, not directly from AP Classroom. I got a similar one from AP Classroom, and I just changed it. I changed it slightly. I think I changed the derivative here. It was the fifth derivative. I think it was the 4th derivative, but since we've had several other 4th derivatives, I just changed it to the 7th derivative. Okay? And using the 6th degree Taylor. Let's do another one. The Taylor series for a function f about x equals 2, that's our c value, right, is given by this expression. So they're giving us the Taylor series. This is the Taylor series. And converges to f from 0 to 4. Nice. If the third degree Taylor is used to approximate f of 9/4, what is the alternating series error bound? Oh, not Lagrange, alternating series. Alternating series is even easier because it is exactly the first unused term. So all I have to do is go get the unused term. So the third degree polynomial is used in the approximation. The first unused term will be the fourth degree term. The fourth degree term will be when n equals 4, so I'm putting 4 in for every n. Okay? I don't need to worry about the -1 to the n power because error is always positive. Okay? So n will be 4. 3 times 4 plus 1 is 13. X minus 2 to the 4th power, where x is 9/4, divided by 2 to the 4th power. That is the alternating series error bound. And we just have to clean it up a little bit here to get it into one of these forms. So let's see, 9/4 minus 8/4 is 1/4. And then I'm just going to pull the 4 to the 4th down to the bottom. And which one of those? I think we're looking at C here. So C. All right, one more here. Okay, f has derivatives of all orders. The third degree Taylor polynomial for f about x equals c, x equals 3, that is our c value, is used to approximate the value of f of 2.5. That will be our x value. A partial graph of the fourth derivative is shown on the right. It is known that the graph has a horizontal tangent line at x is 3.5, so there's a horizontal tangent line there, and that the points 2.52 and 3, 2.8 are on the graph. Okay. Use the Lagrange error bound to show that the error in the approximation for f of 2.3 is less than 1 over 128. Okay, so this would be more of an FRQ style because we're showing something to be true. So the first thing I'm going to do is write the Lagrange error bound. Okay, so I start with the derivative. So I want the maximum that the fourth derivative can be, specifically between 2.5 and 3. 2.5 and 3. That's all I want to know. They gave me more than I need to know here. We don't need this. We don't need that at all. I am only looking at from 2.5, the x value, to our center value. What is the highest that that can be? Well, the highest that that could be occurs right here. They gave us that point that was 3, 2.8, so the highest it can be is 2.8. So 2.8 is the maximum fourth derivative times x minus c, 2.5 minus 3 to the fourth power divided by 4 factorial. By the way, this would be negative, so if this, here it doesn't matter because we have an even power, but if that was an odd power, I would just slap some absolute values here and call it good. Okay? That is the Lagrange error bound. And we're supposed to show that that is less than 1 over 128. So I want that to be less than 1 over 128. That's it. That is it. If you are unsure, if you want to go check it out and make sure that this is indeed less than 1 over 128, go off to the side. You'll have plenty of space. I didn't leave a lot of space here, but go off to the side. Make sure that that is less than 1 over 128 if you want to. But if you don't want to, if you don't have time when you're on the AP exam, you just leave it right like this and call it a day. You'll get full credit. Okay? Alrighty, so that is, make sure I don't have anything more back here. Nope, that is Lagrange error bound. Okay?